This is example 5-5, flow from a tank. So you can see our setup right here. We have a tank that's closed but has a pump on it, and that pump regulates what the pressure is at the top here. It says that it's 40 kilopascals, and then we have an outflow at the bottom where the water flows out freely. And so now we're asked to figure out what the discharge is here. And what we'll do is we'll use Bernoulli's equation, and we'll take something up here, call that point B, and we'll say the streamline goes something out here and then out there, right, until point A. So that's all good. Now if we want to use Bernoulli's equation, of course, we have to make sure they're on the same streamline. So we can say that A and B on same streamline. We know that we have to have an ideal fluid. In our case, we have water, so we have an ideal fluid. And what else? We want to have steady flow. Right, so that means the velocity of these should not change over time, which I think we can make the argument of, right? Because the pressure up here is always going to be the same, so the outflow there should be the same. Now the water level is going to drop, but I think we'll assume that it drops very slowly. So maybe we'll go and write our Bernoulli's equation here, right? So we'd have, if we start at B, right, we can say PB over gamma plus BB squared over 2G plus ZB, and that would be equal to PA over gamma plus VA squared over 2G plus ZA. Just about fits in there. Excellent. Now let's go through and figure out what we have, right? We know what PB is, right? It's given to us as 40 kilopascals. 40 kilopascals, that we know. VB, what do we know about VB, right? Remember that we're talking about the velocity that's going downward. Now, if we're going to say that this tank here is relatively big compared to what this outlet is, right, then remember kind of the reservoir assumption is that this water level is going to drop very slowly compared to how fast it goes out here. So our VB is going to be much slower than VA, and it's squared, which means that we can assume that it's equal to 0. Right, so we can say, or I would say water level better than surface. We can say water level in tank drops very slowly compared to outflow, which means we can say VB is equal to 0. All right, so we have VB. Then we have to set ourselves a datum. Now H is given for it looks at the center of this outlet pipe. So let's say datum is at center line of outlet pipe. Yep, no, outlet pig. That'd be interesting. It's like the Simpsons where the pig gets stuck in the outlet of the reservoir. Outlet pipe, right? So that means for us at ZA is right there, right? That would be exactly that location. So that would be 0. And ZB would be just H, right? And we're given H as 5 meters. All right, so we know PB, VB, ZB, PA we know as well, right? Because PA is going to be, point A is in contact with atmosphere. Point A is in contact with atmosphere. which means that PA is going to be 0. Right? Again, atmospheric pressure, but we're talking about gauge pressure here, so that leaves it to 0. All right, so we have PB, VB, ZB, PA, VA is what we're trying to get, and we have ZA. So we have all our different values. Maybe we can sketch that in here now. So PB is known, right? We can say maybe do it here. 40, let's make this an actual 40 kilopascal. We know VB is equal to 0. We know ZB is equal to H. PA is equal to 0. VA we're interested in. And ZA is equal to 0. Well, that means pretty much everything drops out, which is of course exactly what we want. So what are we left with? We are left with, on the one side, PB, let's just leave that as PB for now, over gamma plus H. And then on the other side, we are only left with VA squared over 2G. All right, so we can want to have VA, of course, so we can get our flow rate. So if you solve that for VA, we'll need VA, not VA squared. So VA is then equal to what? That would just be 2G times, PB over gamma plus H. What can we do with that? Not a whole lot, I think, so we'll just leave it as is. And so that means we can then say our Q, our volumetric flow, right? That's just going to be VA times AA. VA, what we have here, so let's do AA, is another circular outlet, so pi over 4 times dA squared times 2G of PB over gamma plus H. And all of these are known to us, so we can just plug all that in. So that's pi over 4 times, let's see what our diameter is, 0.15 meters, already given to us in meters, squared times, and now 2 times 9.81 meters per second squared. Now we could have taught the G in with a gamma, but then the H doesn't work, so we'll leave it as is. So that is 40 kilopascal, so 40 times 10 to the 3, switch that right to Newton per meter squared. Gamma is 9,810 newtons per meter cubed, and then H was given to us as 5 meters. Now we want to have a flow rate coming out, and if we put the numbers in, we get 0.23583. Should be meter cubed per second. So let's see. Outside of the root, we get square meters. Inside, we get Newton meters squared over Newton meter cubed. So that's a meter. That fits to the meters of the 5. So we're left with square meters over square seconds. We take the root, we get cubic meters per second. So if we round it to 3 significant digits, 2, 3, 6 meter cubed per second. And that's our flow rate. All right, so this is a flow rate that we found if we have a pump generating a pressure at the top of our tank here, and we get a constant outflow.